process capability, and Six Sigma. When we create control charts, which are part of statistical process control, we make sure the processes have today the same variability as they had in the past. So basically, when we say the process is in control, we basically say that it has similar random distribution for some of the important parameters as it had in the past, right? We say the variability is the same, it's not bigger, not smaller, right? So when we say basically in statistical process control, process is in control, the variability did not change, there is nothing unusual about the process. But that doesn't mean the process is sufficiently good. Maybe the variability is so large, we consistently produce bad products, or maybe we consistently deliver too many services that are of poor quality, and all the time we have dissatisfied customers, right? So process capability is actually the part of establishing, or the tool that we use to establish if the process is sufficiently good for what is expected, for the quality level that we actually expect. So from the perspective of manufacturing, there is something called design specification, right? If I have a measurement that I want to be within certain limits, we put what we call a lower specification limit and upper specification limit. For short, they are called LSL and USL. Notice that just one different letter from the control limits. It's not control limit, it's a specification limit, right? Sometimes engineers will put a target value, right, which is like a middle between those specification limit and the tolerance. And the tolerance basically will say how much above or below the target we can move. And again, notice these are not control limits that are limits of variability calculated based on the actual variability. These are desired limits. These are specification limits that we never want to go outside of, because if we do, we say the product is of poor quality or insufficient quality. So in order to establish if the process is capable, if it is sufficiently good, we can calculate the process mean and standard deviation, right, mu and sigma, and then we can calculate this either process capability ratio or process capability index. They're actually very similar and they calculate similar things, but they have some technical difference. Capability ratio is taking the upper specification limit minus lower specification limit, and this difference, right, so like 2 times the tolerance, divided by 6 sigma, and index is taking upper specification limit minus mu and taking mu minus lower specification limit, right, and taking whichever of those values is smaller is adopted here, and it is divided by 3 sigma. So what does capability ratio or capability index actually mean? So what I want you to see is that what we compare here on the numerator is actually the distance between upper and lower specification limit, which is twice the tolerance. So basically we have here 2 times the tolerance divided by 6 sigma, or the tolerance divided by 3, right? This is 2 times tolerance, so if you simplify that, that's tolerance divided by 3 sigma. So basically the ratio is comparing how much larger is the tolerance compared to 3 sigma, or how small the variability is compared to the tolerance. The larger the ratio, the better, because we say the tolerance is wide compared to 3 sigma, 3 sigma being the measure of variability. And this is actually calculating the same thing. You see here there is 3 sigma in the numerator, but here we're actually looking at the part of the distance between the mean and the upper specification limit and the mean and lower specification limit, which is supposed to be the tolerance if mean is in the center between, right? Both of those would be tolerance if mean is exactly in the center at the target value, right? In the center between the lower specification limit and the upper specification limit. But if it's not, this will choose the lower of those values. So this will choose kind of the worst case of the two. For example, if mean is closer to the lower specification limit, this value will be smaller, and so this value will be ignored, and then the index will compare the smaller value to 3 sigma. So again, right, it is comparing somehow the tolerance to 3 sigma, but index is also taking into account situations where mu is off target, is somewhat lower or somewhat higher than the target, and then the index will actually be smaller in that case than the capability ratio. So why are these ratios or indices useful? Well, because we can, for example, decide that a process is capable if the value of the ratio or the index is at least 1. Now, this is what has been done in the literature in the past, and actually notice that CP is only good if you know that your process is centered and you only want to control variability. So if your mu is close to the mean of the right upper and lower specification limit, which is actually equal to the target value, right? If it's close. If it's not, better use CPK, right? If the mean can vary. Now, this capability of 1 was considered to be sufficient, but notice that even if the process is centered, that means you have still, right, if the tolerance compared to 3 sigma is still is 1, right, then you still have a probability for defect 0.3%. So that means out of 1,000 units, 3 units will be defective, or out of 1,000,000 units, 3,000 will be, around 3,000 will be defective, right, statistically speaking, right? So the Six Sigma methodology postulates that we increase this requirement, right? The process capability, process is capable according to Six Sigma, or Six Sigma capable, if the capability ratio is at least 2, and this ensures that there's much fewer defects. There could be 3.4 defects per million opportunities, so much less than 3,000 in the capability 1, and that is even if mu is off center, is not at the center. It's 1.5 sigmas of the center. Of course, if it's less of center, this ratio of defects will be even smaller, and the number of defects will be, in fact, much less. So let's consider an example. If we assume that we have the scooter steer support, the part that we produce, and we assume that we measure the height, that is the critical measurement, and this measurement, right, this height should be between 79.9 millimeters and exactly 80 millimeters, right? These are the specification limits, right? Let's say we measured 125 units that were produced, right? And we found out the mean of those is 79.95116, right? It's actually slightly off center, but very slightly, right? This 116 here is the additional value, right? The center value between 79.9 and 80 is 79.95. So this is just slightly above, right? So we seem to have a centered process, almost centered process. And the standard deviation based on those 125 units is calculated here, right? So we can now calculate the process capability ratio. We take upper minus lower specification limit, so that will be, right, this value 80 minus 79.9, that's going to give us 0.1, and we divide it by 6 sigma by 6 times this value, we get 1.917, or if you calculate capability index, right, we take the minimum of those two values. Of course, now mu is a bit above the target, right, the central value, so this value will be smaller, right? So this value will be taken. It will be something like 0.0489 or 88, 0.04884, right? This value will be slightly above 5. So this value will be taken, divided by 3 sigma. It will give us 1.873. Both measures, as you can see, are more than 1. So according to the rules, we say process is capable of producing according to specifications, but right, it's actually more than 1, much more than 1. But both measures are not at least 2, right? So process is not 6 sigma capable, but actually it's quite close, right? This is very close to 2 or this, right? And of course, the difference you can see here, this is a bit lower, this is a bit more conservative measure because it's not just looking at the distance and comparing it to 6 sigma or tolerance, right? Half of that is tolerance, comparing it to 3 sigma. It's actually looking at the side of the variability that is closer to the more likely to exceed the upper specification limit or go below the lower specification limit, and dividing it by 3 sigma. And because our mu is somewhat is slightly above the mean, then right, this is going to take this value and divide by 3 sigma and gets it slightly less than 1.9. It's 1.873. And of course, this means that the capability here is a little bit smaller than required by 6 sigma, but actually it's quite close, and we will probably have very few defects per million opportunities, or using another measure. The number of defects would be quite small.